오케이. 자, 그럼 시작해 볼까요? So in the last class we have learned how to calculate the how to calculate Gibbs energy, enthalpy and entropy, okay? And let's go back a little bit more again, okay? Because I think some of you probably could not follow it well because we really did it very quickly. So let's go back again, okay? So this is chapter 2, I think section 4, calculation of the Gibbs energy, okay? So let's go back to the enthalpy again, okay? So enthalpy, H at the given temperature. So Gibbs energy at the given temperature is H at the given temperature minus Ts at the given temperature, basically. So, for example, Gibbs energy of the I species at given temperature equal to enthalpy of I species at given temperature minus T entropy at the given temperature. Is it okay? And then because this is we are actually talking about the pure stoichiometric material, not the solution. So theoretically we can put this not, which tells this is the stoichiometric compound. Okay? Now H, so H at the T is typically defined by the delta H 298 at the plus integral heat capacity dt from 298 to the certain temperature if there is no phase transformation. Okay? And we call this H here as standard enthalpy of formation. Okay? As I mentioned, enthalpy, there's no absolute value, so we actually make a reference. We choose some reference as 0, and then based on that actual value, we recalibrate enthalpy value. So that's why we have delta, and so that's why we say it's a formation from the pure elemental species. Okay? So standard enthalpy of formation. Why we say standard? 298 Kelvin, and then also this is stoichiometric compound. So that's why we say standard enthalpy of formation. Okay? And entropy at the given temperature was S 298 Kelvin plus integral Cp over the T dt from 298 Kelvin to the certain temperature. And then this one here, we call this one again standard entropy. There's no standard entropy of formation because this is absolute value, standard entropy, okay, of the given material. And of course Cp is the heat capacity, and typically if this is 1 mole, then we can make, instead of big H, we can use the small h, molar enthalpy at the given temperature is standard molar enthalpy of formation plus molar Cp. Okay? And same thing, standard entropy of formation, standard entropy at the given temperature, standard entropy, molar standard entropy plus integral Cp over T, and Cp is the molar heat capacity in that case. Okay? If you have the many moles of that, you can just multiply that n moles of the standard molar enthalpy plus m moles of Cp. Then you can get multiple moles of the material. Is it okay? Good. And when you look at actually this one again, so let's look at this and this way. So let's assume this is temperature, and then this is H of the material at the given temperature. Okay? In this case, it's pure, so H naught. Okay? And in order to calculate this one, if I represent this actually the equation in the graph here, we can just define it this way. Okay? So at 298 Kelvin, we have our value here, delta H at 298 Kelvin. So standard enthalpy of formation at 298 Kelvin. And then if I make an integral I'll have integral value here. So this is change of the h, or strictly speaking, it may not be straight line. So you can have something like this, and this is the heat capacity at each temperature. So the slope of this curve is heat capacity. Because this is h curve with the temperature. And if you make a derivative of h curve with the temperature, this is constant, so it's 0. And you can get the heat capacity, basically. Is it okay? And now, if somebody say, okay, I want to calculate delta H. So this is different, not delta H 298 Kelvin. Delta H from A temperature, so for example, 500 degree Kelvin to 1000 degree Kelvin. So this means this is H at 1000 degree Kelvin minus H at 500 degree Kelvin. So if I actually show the H at 1000 Kelvin, so H at 1000 Kelvin is delta H 298 plus integral Cp from 298 Kelvin to the 1000 Kelvin Cp dt, and then minus H at 500 degree Kelvin. So it means this value plus integral 298 Kelvin to the 500 degree Kelvin. So eventually this will be same as integral of Cp dt from 500 degree Kelvin to the 1000 degree Kelvin. Okay, good? So basically in this graph here, we can say, okay, let's take 500 degree Kelvin, and then let's take 1000 degree Kelvin, and this difference here is delta H from 500 degree to 1000 degree. Is it okay? So this difference. Okay? Is good? Now, if you actually apply this one to the another one, when you have now phase transformation, okay? So let's assume now this is temperature, this is H at given temperature of the material, and then let's assume, okay, I have phase transformation. So this is solid 1 of my material. So ion BCC phase, for example. And then ion FCC phase, solid 2, different crystal structure. And then this is liquid phase, for example. Okay, we can have this one, yeah. And this one here, slope here is Cp of the solid 1 state. Okay. And slope here is Cp of the solid 2 state. So FCC ion or BCC ion, FCC ion could have different heat capacity here. And then this one is Cp of the liquid state. Okay, good? And then now, so this value here, so this is delta H of the I species at two, so solid 1, theoretically solid 1 at 298 Kelvin. Standard enthalpy of formation of the solid 1 phase at 298 Kelvin. Good? And even though I don't know exactly what's the standard enthalpy of the solid 2 at 298 Kelvin, from the heat capacity curve, from the enthalpy curve here, if I can make a kind of extrapolation, I can make extrapolation of this H as a function of temperature, and then I can have this one here now. So this is delta H of S2 at 298 Kelvin. So imaginary enthalpy of formation of S2 at 298 Kelvin. Is it okay? Most of the time we cannot measure it because this is metastable phase at this temperature. However, if we know the heat capacity function very well, and if we can assume that that heat capacity function can be extrapolated outside of each range of stable range, then we can more or less estimate what will be this value. Is it good? Same way, this is very, very difficult, but we can still make estimation of this liquid phase too, yeah? So here. So this value here, delta H of liquid phase at 298 Kelvin. So standard enthalpy of formation of liquid at 298 Kelvin. Is it okay? So now, in order to calculate, for example, this value here. So I want to calculate enthalpy of S2 at T1 temperature. So H S2 phase at T1 temperature. I want to calculate this one. Okay? There's many different ways we can do it, depending on the information you have. So, one of the first one. Okay, very simple one. If I know this one, this curve, if I know this one, I can start from here and then just make integral up to this point. So basically, I know this one because I have to calculate basically this one. This is my question, yeah? I know this value. So in order to know that value, I can start from here and then I can go here. And the difference here is integral of Cp of S2 from 298 Kelvin to T1 temperature. Is it okay? So that's the most easiest way. So delta H of S2, it's not S1, S2 at 298 Kelvin plus integral Cp of S2 dt from 298 Kelvin to the T1 temperature. So this is the one of the first one we can do. But as I mentioned, in many cases, we don't know this value, then we cannot use this equation, yeah? Most simplest one, but depending on whether this information is available or not. Okay, second one. Most of the time, we have this information is available. Okay, so now, I want to start from here and I want to calculate this one. Okay, so then, one of the things we can think about is, okay, here to here. So then it means, so up to here, so this point to this point, this difference is integral Cp of S1 from 298 Kelvin to this transition temperature. Okay, so let's take this one is T transition 1, and then let's take this one again, T melting. Okay, so it's a solid transformation, S1 to S2, and then this is liquid, solid to liquid, melting, okay? So, this difference here, that's integral Cp from here to here, okay? So, if I know this one, I add up this one, and then I can add up this additional one, delta H of transformation, and then from here to here, I can just do the integral of S2 between that two ranges. So this one, and then this one, 3. So this is basically H here. So this is delta H of transformation, and this is delta H of melting. Is it okay? So we can do this, and we can do this. I mean, we can take this one, and then I can add a very small part here. Then I can calculate this value here. So I start from here, and then I add up this one, and then I add this one, and I add this one to get this value. Okay? I mean, graphically you can understand this one. Then if I express this one, it will be delta H naught S1, yeah, at 298 Kelvin plus integral from 298 Kelvin to the T transformation 1 here, Cp, in this case S1, yeah, we are just doing this part, Cp of S1 dt plus this difference, delta H of transformation plus the last part, Cp of S2 dt from transition temperature 1 to the final temperature T1. Is it okay? So this is another way. Is it okay? Now I will show you a very interesting third way. For some reason, let's assume I know this value. I know this value. Okay? So, this value here is, I can calculate this one up to this one. So I'm starting from here to here, and then I just take out this amount, and then I take out this amount. Do you get it? Just mathematically. Okay, I start from here, I want to go up here, and then go down up to this one, and then go down further. Then I get this one. That's possible too, yeah, mathematically. Sometimes we are using this equation too. Assuming the supercooled liquid phase is available, and then I have to go to the other cycle, and then coming back to the lower temperature. Okay? So in this case, delta H naught of liquid phase at 298 Kelvin. So that's my starting point. And then I'm going up to here. So it means integral 298 Kelvin to this point is melting temperature, Tm of Cp, in this case, liquid phase, Dt, plus, now I'm cooling down this one to this one. Okay? Then this will be delta H of melting, but it should be minus here because I'm going backward. So delta H of melting is typically positive number. This I'm coming down, so it's a negative number. And then plus, now I'm cooling down from here to here. Okay? So integral Tm to the T1 temperature, Cp of S2 dt. So this value should be negative value, yeah? Because Tm is higher temperature than T1, and Cp is always positive. Okay? This is also exactly the same. So this actual equation can give exactly the same value we need for the S2 at T1 temperature. Okay? So it's really depending on the available information, you can make any different equation. But key information is delta H of the different temperature, delta H change. We call typically this one is and heat content change from T1 temperature to T2 temperature. Okay, that's integral of Cp dt from T1 temperature to T2 temperature. So how much heat I need to change my material temperature is integral of Cp dt. Okay, that's the baseline. You good? You can do the similar thing for the entropy. So entropy equation is same, so you can do exactly the same way. Is okay? We'll practice a lot of this one during your actually the exercise and then your homework. Good? So now, let's go back again. So this is for the given material, okay, at the given temperature. So what's the Gibbs energy of given material at the certain temperature, and what's the given material enthalpy of given material at certain temperature, and etc. And now let's look at one more interesting thing here. So let's take Gibbs energy function. Okay, and then this is temperature. So Gibbs energy of the certain material, I, for example. Let's take this is solid, and then let's take this is liquid phase. Okay. So slope of liquid is more steeper than slope of solid because slope is related to the entropy, yeah, minus entropy basically, and then entropy of liquid is higher, so that's why slope is more negative for the liquid phase than the solid phase. Is okay? So we have learned this one. And now let's look at this point at melting temperature. So below this one, solid is stable phase, and above this one, liquid is stable phase. Yeah? So it's a one component system. I have, for example, H2O, ice, water. Okay? At melting temperature, the Gibbs energy of solid and Gibbs energy of liquid should be same. Okay? So, at Tm, Gibbs energy solid should be same Gibbs energy of liquid. Then there's the phase transformation. So when you are reactant solid, product liquid, when you have same energy, two phase can exist together. Is it okay? Because both of them have exactly same Gibbs energy. So both phase can exist. That's melting temperature, yeah? Now if I draw this one in terms of enthalpy, so, and then in terms of entropy, it's a little bit different. So at this actually the melting temperature. So as you can see, this graph, typically solid enthalpy have lower value than liquid enthalpy. Yeah? So I have solid enthalpy, and then here I have transition, and then I have liquid enthalpy. So this is solid, and this is liquid. And we know this difference is delta H over the melting. Yeah? So, in terms of the Gibbs energy function, it's kind of continuous function. So this is stable in terms of liquid phase. This is stable, and then Gibbs energy changes this way, yeah? But it's continuous. Slope is changing at certain point abruptly, but however, the change of actually the Gibbs energy itself is continuous. In case of enthalpy, we have this continuity here. So this value, and then suddenly this value, yeah? Okay? And then in terms of entropy, we'll have solid entropy, and then we'll have liquid entropy. So at transition here, we have delta S over the melting. Yep. And entropy of solid should be lower than entropy of liquid phase. So we have this kind of graph. Okay? So now, if I actually apply this one, so solid Gibbs energy and liquid Gibbs energy is same. So this means, so solid enthalpy at this temperature is H of solid minus T at the melting temperature of entropy of solid. You correct? That's Gibbs energy of solid phase, yeah? This is same as H of liquid minus Tm S of liquid phase. Yeah? At the Tm temperature, this should be same. Then I can just I can move this one to this side, move this on this side. Then we can have delta H of solid become liquid at Tm temperature equal to Tm delta S solid become liquid. And this value here, basically delta Hm. Yeah? This is enthalpy of the melting. Solid become liquid at this Tm temperature. So this value. So delta H of melting. Enthalpy of melting, yeah? Enthalpy of fusion, enthalpy of melting. And this one, same thing. Delta S of the melting. So we can find actually the one relationship here. So this bring delta H of the melting equal to Tm over the melting delta S of melting. Or in general, delta S of transition, so any kind of transition, melting is one of the transition, yeah? Solid become liquid phase, that's transition, transformation, yeah? Equal to delta H of transition divided by temperature. This is important. Okay? We can find one relationship. Is it okay? Any kind of phase transformation or phase transition, when you have at that transition temperature, this should be applied all the time. Okay? Good? And this is why I want to say this is important is sometimes we give the H298 value and then face the delta H of transformation value, and then we give also temperature, and then we do everything. And then when you have the entropy value, we have entropy at 298 Kelvin, and then CP function, and then there's no information for the delta S of transformation. Then we cannot calculate, the entropy of the material at the second phase. But however, because we have this relationship, we're supposed to know that the delta S of transformation should be related to the actual delta H of transformation. So people don't provide that additional information, but you have to actually get it by yourself. Is it okay? So if this information is given, even though you don't have this information, you have to know how to calculate it, or the other way around. Is it okay? And we're going to actually introduce two different laws later, and that's actually the relationship of this one, the transformation entropy. So when you have solid become liquid phase, for example, we have FCC structure material, and then it become liquid phase. Entropy is depending on the crystal structure. Yeah. So FCC, whatever is temperature, okay, when it actually transformation from FCC to the liquid phase, liquid, regardless of the element, liquid should be similar, yeah, similar structure, and solid, regardless of element, FCC crystal structure is same. So that transition, the entropy of the FCC material, whatever it is, entropy of whatever liquid phase, it should be same, similar, not same, but similar. So the difference between FCC become liquid phase, of the entropy difference between FCC to the liquid phase, there should be some general value, regardless of the element or species. Okay? Same thing. For the liquid become gas phase, gas regardless of whatever element you have, and then liquid become gas phase. The structure change is almost same. So there should be some general value, one general value, reasonably similar value for this liquid become gas phase. The entropy of transition have certain value for the solid become liquid and liquid become gas phase. And that's actually, that was actually experimentally proven, and we're going to look at it very quickly for that information. Okay? Good? Okay. Now, okay, so I'll just show you, all this information, but then how about actual value? Okay, that's actually the value. You can see it in your handout. So I gave you handout. Can you open your handout? Okay, I think you have 4 pages. So I think you have to look at first one, this one. Can you find some table which contain this information? I think it's probably one of the first one. Okay. And let's look at this one. So in the very first actually so this is standard Gibbs energy of reaction. Okay. So for example, you have any kind of reaction is written here, and then there's delta G. Yeah. Do you see that? Okay. So let's take the very first one. 2 moles of Ag, 2 moles of silver, solid phase. This is very important, solid or liquid. You have to know exactly which state it is. Otherwise, your Gibbs energy is different, yeah? So 2 moles of Ag solid plus half moles of oxygen gas become Ag2O solid. Okay, good? And for that actually Gibbs energy of reaction, that reaction, delta G of reaction equal to those value. Okay? So let's take this one. So, I mean, everything we have seen so far was only for one component material, yeah? So, I mean, if I have given material, what's the Gibbs energy, yeah? But this is already chemical reaction, okay? So then how can you calculate such thing? So, A plus, for example, B equal to AB. So let's assume this solid, 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 okay? So, delta G of reaction, because it's chemical reaction equal to basically Gibbs energy of AG, AB, solid phase, pure, minus, so product minus reactant, yeah? Gibbs energy of A plus Gibbs energy of the B. And this one, we know that H minus TS, H minus TS, H minus TS. So in the end, if I just make a graph here, so this is Gibbs energy of I, for example, and temperature. Then let's take this is Gibbs energy of A, solid phase. And let's take this is Gibbs energy of B, solid phase. And then let's take something like this is Gibbs energy of AB. I'm sorry, this is ridiculous. So this is ridiculous too, sorry. So this is Gibbs energy of A, solid. Gibbs energy of the B, solid. And then let's take this one is Gibbs energy of AB, solid phase. So at the given temperature, this Gibbs energy minus this one. That's a delta G of formation. Delta G of reaction, yeah? You good? And then if you make those things, then you can have basically delta G of reaction like this. And then you can make a plot. Typically, this graph, so with the temperature, unless there is any phase transformation in the reactant or product, if there's no phase transformation in the reactant or product, the graph here is reasonably straight line. It's not exactly straight line, but it's quite similar to the, quite close to the straight line within given temperature range. Okay, so this typically A plus BT. Is okay? And then when this is A plus BT, basically, then delta G of reaction equal to delta H of reaction minus T delta S of reaction, yeah? So we can take this one from here, and this one from this one, minus T delta S. B equal to minus T delta S, A equal to delta H. Is it okay? Okay? And depending on whether this A equal to solid or liquid phase, solid, liquid, or gas phase, the slope here, delta S, is quite different. Okay? Because the slope here is depending on the state here, the solid or liquid or gas phase. Gas phase, much steeper. Yeah? Entropy is much smaller, much bigger, sorry. So when you have chemical reaction, for example, solid phase, gas phase becomes solid phase. Then reactant have much higher entropy. Solid, whatever solid it is, I mean each crystal have certain crystal structure, so the entropy is reasonably small. But if it becomes gas phase, suddenly entropy is jumping. Okay, it's much bigger entropy. So if you have chemical reaction have solid, gas, become another solid phase, then entropy of reactant have much bigger value then entropy product. So entropy product minus entropy reactant should be negative value. Am I right? And negative value. So this is negative value, then negative, negative plus positive value. So B term should be very positive temperature. B should be positive value in that case. So as you can see here, first one, Ag plus oxygen become Ag2O. So in the reactant, we have gas phase, and product there's no gas phase. So the B term, 66, it's a very big positive number. If this is delta S minus delta S of reactant or reaction, okay? And same thing for the aluminum. So 2 moles of aluminum plus third one, 2 moles of aluminum liquid plus 1.5 moles of oxygen gas equal to Al2O3. You can see that the B term is very big positive term, yeah? Everything is gas phase. So, and then let's go to the somewhere in the middle here, iron. So can you see this one? This is solid become solid phase, yeah? So solid iron plus solid carbon become solid iron carbide, Fe3C. The value there is negative even, yeah? It's not positive because it's really now solid actually the kind of entropy change, okay? Most of the time close to zero, become solid become solid. It's close to zero, but sometimes negative, sometimes slightly positive, okay? Depending on your real entropy or heat capacity, okay? But it's close to the zero. That's actually important. Okay? Good. So if you know the one component Gibbs energy, you can easily calculate the reaction Gibbs energy. Or if you know the one component enthalpy or entropy, you can also, of course, easily calculate the reaction enthalpy and entropy. Is it okay? Good. And let's look at very first one more time. So Ag, 2 moles of Ag solid and this one delta G and this is minus 30.3540 plus 66.1 T. Okay? So typically say joule, and the unit is joule, yeah? Or we say joule per mole of formula. So this formula is this value. If I multiply this one by 2, this should be multiplied by 2. It's a per mole of the given formula. Okay? So you can say joule, but strictly speaking, joule per mole of formula. Okay? So it's a bit strange in terminology, but people actually using it in this way. Joule per formula or joule per mole of formula. Okay? Or joule per mole in general. Okay? So it's depending on how many moles of material is reacting here. Gibbs energy is extensive property. Depending on the number of moles, your Gibbs energy is multiply with the number of moles of the system. Okay? Not the temperature, not the pressure, but Gibbs energy, enthalpy, entropy, all this one is extensive property. So it actually extended with the number of moles of your system, the size of your system. Yeah? Okay, now let's look back this one more time. There's actually another important information here. At 298 Kelvin, okay, delta H of reaction at 298 Kelvin is this value, yeah? Because it's regardless of temperature. Delta H is not changing at the moment with the temperature. It's constant value. Delta S is also constant value, yeah? That's actually the definition in this equation. Our test, we can see it from this equation. And at 298 Kelvin, your H of Ag solid equal to 0. That's a standard state. Am I right? H of O2, 0. at 298 because this is standard material, standard reference material. So delta H of reaction is same actually. Delta H of reaction here is same as delta H of Ag2O solid at 298 Kelvin. Standard enthalpy of formation of Ag2O. Is it okay? I mean, for some reason the chemical reaction is given in this way, and we have H value, delta H value, and theoretically, if you just apply our theoretical equation, then delta H of Ag2O solid at 298 Kelvin, the standard enthalpy of formation of Ag2O from our reference material is exactly the same as delta H of reaction in this case. Is it okay? So we can get additional information here. Good? Okay, so anyway, this is how we're actually looking at. And let's look at next one. So can you find this one? Probably it's on the third page. Yeah. Or third page or fourth page. I think we have to go one more. One more. So last page. Last page on the left side. Last page on the left side. Because I just only show only the sum of the beginning of this heat capacity table. So this is the one of the table you can actually see it for the heat capacity. Okay? So molar heat capacity. So it's per mole basically. Per mole of your actual material given here. And the unit of heat capacity is actually joule per mole Kelvin. Joule per mole and then divided by also by Kelvin. Okay? Because Gibbs energy is joule per mole, yeah? So now let's look at this one. G equal to H minus Ts. Gibbs energy, joule per mole typically. H, of course, then joule per mole. This one, and we multiply this one with the temperature, so it should be joule per mole, and then also Kelvin here. Okay? And then H, yeah, delta H, whatever given temperature, H minus H something equal to this one. So it means Cp should have joule per mole Kelvin 2. Okay? So you have to be careful about unit. Okay? So if I don't provide you the unit, it means I give it wrong information. You have to know exactly what's the unit of your energy. Is it joule per mole or joule per gram or calorie per mole, calorie per gram? I mean, I can give any information, yeah? So if there's no unit, you can directly say to the person, you give wrong information. The information is not sufficient to calculate anything, you know? Okay? So here, heat capacity, it says that if you look at actually the table here in the beginning, or the heading of this table, Cp, molar heat capacity at the constant pressure, equal to A plus Bt plus Ct minus square function. Okay? And then, that's good. I mean, so ABC, if I plug in ABC from the table, I should get what's my heat capacity of material, yeah? But typically, it also gives you in this way. So heat capacity is A is this value, B times 10 to the 3 is this value, and C times 10 to the minus 5 is this value. Okay? What's that mean then? I mean, so I have to now know what's the real B value, what's the real C value. A is easy, as it is, and B and C, what's my value? So look at this one. So B times, for example here, B times 10 to the 3 is this value. It means B equal to 8.54 times 10 to the minus 3. Am I right? Okay? So in general here, AG solid, for example here, very first one, Cp of AG solid equal to 21.3 plus 8.54 times 10 to the E minus 3, 10 to the minus 3 times temperature plus 1.51 times 10 to the 5 T minus square. Is it okay? And joule per mole Kelvin, of course. Okay, you have to know how to read the table. Okay? You good? Because those two values, B and C, is so small, so big, so it's, there's no need to actually make, spend your, paper just for nothing. So that's why we just keep it in this actual form. Okay? You good? And then you have this one, range of temperature. So this is really the range. You can apply this equation, this CP equation. Okay? However, so, for example, very first one, AG from 298 Kelvin to the 1234 Kelvin. And 1234, we said it's a T melting. It's a melting temperature already. Okay? Above this temperature, theoretically, you cannot use this equation for the solid phase. However, also from the theoretical point of view, we know that heat capacity cannot be changed suddenly. So it should have certain shape, even outside of that actually the range. So typically we can extrapolate those kinds of heat capacity function above those, those range by about 100 degree or 200 degree Kelvin. We can still use those kinds of the equation. Okay? But if you go to the 1000 degree above that limit, then the heat capacity function may be completely wrong. Okay? But up to the reasonable temperature range, about 100 degree or 200 Kelvin more, is reasonably okay. Because sometimes we have to really calculate those kinds of values. So we can just extrapolate it out. And the other one is all the same. So, and then AG liquid is 1234 Kelvin to the 1600 Kelvin. And then AG liquid, if you look at actually the second one, AG liquid, heat capacity is only one temperature, yeah? A. There's no temperature dependence. Okay? Many cases, liquid have constant enthalpy. Oh, no, I'm sorry. Constant heat capacity, sorry. Not enthalpy, constant heat capacity. But theoretically, it should still have certain actually temperature dependence. Sorry. But many cases only constant because we cannot measure very high temperature. Solid is very easy to actually for the measurement. So we can measure the solid phase very easily. But when you go to the liquid phase, now, all your material cannot sustain very well for the experiment. Experimentally, it's difficult. So that's why we just measure very small range of temperature. So reasonably constant value. And also, because in the liquid state, now all the atom is very, loose actually the bonding between the atom to atom in the liquid state is very loose. So it's very far each other. So even you actually heating up, there's almost no feeling for the other actually the element. So the heat capacity is not really changing that much with the temperature too. It's a very small temperature dependence typically. Okay? Because it's not really tight bonding to make a vibration. There's no restriction for the vibration anymore. So heat capacity is reasonably constant with the temperature in the liquid state. It's same for the gas phase, yeah? Okay? And so that's why it's almost constant, but theoretically speaking, it should have certain temperature dependence term. Okay? And then it show you only about 1600 degree Kelvin. Even above this one, there's still liquid phase, but it's just measured at that limited temperature range. Okay? So that's all good. And then if you go down now, you can see that this one. Okay. Graphite. What's this value? Okay. So this means I want to express most of this table, most of this heat capacity, A plus BT plus CT minus square. But however, for the graphite, we cannot really express each heat capacity by using only three functions. Only three constant value here. So that's why we have to add additional temperature dependence term. So that's the additional term here. Okay? So graphite, we have to say 0.01, heat capacity is 0.01 plus 38.94 10 to the minus 3 with the temperature product with the T, and then minus 1.48 10 to the 5 T minus square minus 17.38 10 to the minus 6 t square. We need 4 terms. That's what it means. Okay? So we add actually additional term here. Is it okay? So this is how does it work, how you have to read actually this kind of table. Okay, now, so let's just we know the heat capacity. Now let's move on. Now this is standard molar heat of formation. So standard enthalpy of formation. Same thing, heat is same, enthalpy. So most scholastic term, it's enthalpy. Standard molar enthalpy of formation, joule per mole. And then standard molar entropy, not formation, standard molar entropy, because it's absolute value. Okay, Al2O3, look at Al2O3, the very first one. Delta H not at 298 Kelvin, joule per mole equal to 1,675,000 and then 700. Yeah. So it's 1675 kilojoule per mole, more or less. Yeah. Okay. That's delta H 298 Kelvin for the Al2O3. So if I want to calculate Gibbs energy of Al2O3, then we have to start from this H298 plus integral blah blah blah. Yeah. And then S value, S298, 50.9 joule per mole Kelvin. Joule per mole Kelvin, yeah. And the barium, second one, barium, delta H, there's no information. Because barium, especially this is solid phase. If there's no information, it means it's a solid phase. And barium solid at 298 Kelvin. Delta H of 298 Kelvin should be 0, because that's our assumption, yeah? It's a reference material. So that's why you don't even need that information, 0. And then S is absolute value, so we have 62.4. Is it okay? Can you read it now? And then graphite, if you look at graphite and diamond, let's look at these two. So graphite, H298, 0. Delta H298, 0. However, diamond is the 1900 joule per mole Kelvin. Joule per mole, sorry. So it's positive number, yeah? And then S298 is quite different, actually, between these two materials. And then if you go to the nitrogen and oxygen, in the very bottom, you can see the same. Nitrogen gas phase at 298 Kelvin. H is 0, H298. Delta H298 Kelvin is 0, because this is reference elementally stable phase, yeah, at 298 Kelvin. And then oxygen is same. But if you look at actually the entropy term there, the gas phase entropy is much bigger than any solid phase. You know, gas is much looser structure, much higher entropy. You good? Everybody good? Next one. Now, this is molar enthalpy of melting, heat of melting, molar enthalpy of melting, or molar entropy of melting, for example, if I know the temperature, yeah? So AG transition is the solid become liquid transition, okay? And delta H transition, so solid become liquid phase, so it means enthalpy of melting, yeah? So enthalpy of melting is 11.09 kilojoule per mole, okay, at that given temperature. Is it okay? And then Al2O3, so look at it. Al, Ag and Al, solid phase. And then you see that Al2O3 solid phase. Now it's oxide, yeah? So Ag was metal, aluminum was metal, which is reasonably smaller value. Al2O3 is much bigger value, yeah? 100 kilojoule or 107 kilojoule per mole, more or less, yeah? And of course the melting temperature is also much, much higher. Okay? And then if you look at the barium, there's the two. So barium alpha to beta transition. So it's a solid to solid transition. And that's very small number, 630. Solid to solid. I mean, just change a little bit of each crystal structure, yeah? And however, beta to liquid phase, which is solid become liquid phase, have much higher enthalpy of transition. Because now you have to break down all your bond and then become liquid phase, yeah? So that's why you need typically bigger number. And if it is gas transitions, liquid to gas, it's much bigger number, of course. Okay? You good? So you know how to read it. Now, let's go back this one. As I told you, there's actually two laws which actually generally stand for the entropy of transition. You don't have this one. You don't have this one, sorry. Now you have to write down again in your text, your note. Because I need a graph, so that's why I actually put it here. I'll actually show you the graph. Okay? So, there's the two rules. One is Richard's rule, as you can see here, and the other one is Troughton's rule. Okay? It's follow up the person who actually investigates this actually the transition. Okay? So, Richard, basically, the reviewed all the enthalpy of the transformation from solid to the liquid phase. And all this solid is FCC solid metal or BCC solid metal become liquid phase. That's what he did. So he collected all the enthalpy of melting of FCC metal and then all the enthalpy of melting for the BCC metal, and then he plotted with the melting temperature. So y-axis here is melting enthalpy, and then x-axis is temperature. So basically what he did is, okay, delta H of the melting with melting temperature of a given material for the metallic actually species, and he found this one, FCC and the BCC phase. So this is FCC and this is BCC. Okay, and it goes to 0 at the 0 Kelvin, more or less. And when you look at this one, this slope and this slope, so Tm and enthalpy of melting and the melting temperature. So delta S of melting equal to delta H of melting divided by each melting temperature. Yeah? So this slope is basically delta S of melting. Yeah? Is it okay? So this is delta S of the melting of the metallic material. And then he found out that this delta S of melting for the FCC phase has certain value, more or less, and that value here is about 9.1 joule per mole Kelvin, or this one was about 8.25 mole Kelvin. So this one is generally related, okay, I have FCC structure or BCC structure in solid, certain crystal structure, and it become liquid, very loose structure. The entropy change of this one is almost same regardless of your material. If you have fixed crystal structure that actually have certain entropy regardless of your element, and they become liquid phase, then actually have also certain actually entropy value regardless of your element. Of course, enthalpy and entropy is changing with the temperature, but at the melting temperature, we can see that, okay, it's become solid, become liquid phase, and that actually have more or less constant value. If you look at this one, more or less solid become liquid phase, or this is FCC, BCC, even HCP, all those kinds of material, delta S of melting is about 9, roughly, or about 10 if you like. Okay. That's Richard's rule. I mean, theoretically it's very simple, but I mean, in order to show you, in order to show the idea, you have to really collect the information and then show really. And that's what he did basically. The idea is very simple. And similarly, now Truton, same thing. He collect now, okay, how about liquid to the gas phase? Vaporization, from liquid become gas phase, vaporization. And then, or boiling, vaporization or boiling is same idea. And then T of vaporization, boiling temperature. And then he collect all the data, and then he find out that this slope become about 88. So delta S of vaporization, so basically liquid become gas phase, it's about 88. Okay? Yep. Oh, delta H, sorry. Thank you. Okay? So, as we expected, the enthalpy need to make evaporation is much higher value, first of all. And if you actually think about it in terms of the entropy of gas should be much higher than solid or liquid phase. Okay? I mean, if I now combine these two together, Young's rule. Delta S of sublimation, is it correct? Sublimation is something strange. Sublimation, solid become gas phase, will be summation of these two, yeah, more or less. So about 100. Okay? So about, I mean, you have to know reasonably this number. You don't have to remember it, but at least get some idea, okay? So solid become liquid about 10 joule per mole Kelvin, okay? And liquid become gas phase about 90 joule per mole Kelvin, and then become solid to the gas phase. Whatever solid it is, whatever crystal structure it is, reasonably about 100 joule per mole Kelvin. That range. Why we actually say in this way is, as you can see, delta G of reaction is more or less constant, A plus BT. So, of course, there's the CP is important, but if you assume that CP of solid product become liquid, I mean, that solid reactant and the product is almost same. Summation of solid, CP of solid state, our reactant state, and then product is almost same. Then we can just eliminate over delta CP, more or less. Then those values, delta G of reaction is A plus BT, almost constant. Then we can more or less assume in this way. There's some change, but I mean, roughly. So whatever, regardless of temperature, more or less, regardless of material, if you have solid become gas phase, that's about that range. Not like 1,000 or not like 10, about 100 or 100 something, plus minus. Okay? You good? Any question? No? Okay. Yep. It's metals, but actually now you can do the similar thing for the old oxide. So like AO oxide, then you can get actually similar kinds of the also trend too. Not exactly the same value, but there's certain value. Yeah. Is it okay? Now, (1.5). You know Hess's law, yeah, already. Everyone knows Hess's law, probably already. You learned this one from chemistry, general chemistry. I don't want to really teach this one because I mean it's so obvious. So why we can actually apply the Hess's law? From thermodynamic point of view, why do you think Hess's law is working? So Hess's law is basically like this, yeah? I have A plus B become, for example, C plus D. And I want to calculate this delta H of reaction, basically. Okay? And then I can go this one. Or I can go this one. Whatever step you want to go. So H, so this is 1. Whatever you do, delta H, this reaction equal to same as delta H1 whatever sub-step you're taking, the H in general, in the end, the total enthalpy change is same regardless of your path. It's any subsystem, I mean, it's a path, different path here. I'm going this path, I'm going this route, but in the end you actually arrived in this one. Hess law is simply explaining H enthalpy is state function. That's it. Am I right? I mean, your initial condition, your final condition. Okay? The difference of initial to the final condition, whatever path you are doing, it doesn't matter. If your initial condition and final condition is the same, the change of enthalpy is same, regardless of your path. That's basically the definition of state function. So enthalpy, Gibbs energy, entropy, all of them. And Hess simply just proved that experimentally, okay, enthalpy is easy to measure. So enthalpy, at least you have this kind of rule is applied. Okay, so it's basically enthalpy is so you already all know. There's no point actually to go. But sometimes we need this kind of Hess's rule, Hess's law, because we cannot have directly this information, then you have to, based on any available information, you have to make different step and then go back. So in that case, we are still using the Hess's law, but this is basically state function. That's why it happened. Is it okay? It good? Everyone okay? So we finished part 1 of thermodynamics. All the theoretical part. Okay? And next week, we're going to actually do some practice. Okay? So I'll bring up some real example, how we're actually using this kind of information so far to really deal with the real thermodynamic problem in the world, in reality, in real actually the real world. Okay?